Hello, Monday, November 20th, 2023, and we're beginning on problem 4. I prepared by writing the indices which we had from problem 7 in section 3.1. And when n equals 3, this is 4, and this is 2, and when n equals 4, this is 6, 3 halves times 4, that's 6, yes, and 2, 4 times 1 minus 1 half, yeah. Oh yeah, we only have 1 and 3, of course. And here we have 1, 1 and 2, and here we only have 1 and 3. Oops, that should be 4. It's a question of finding the side classes both to gamma naught in gamma and to gamma 1 in gamma. And here we have a total of 8 side classes, and here we have 12 side classes. That was a lot. So let's start with 3. We already know the cusps of gamma naught. We did that in problem 18 in section 3.1. And it was just infinity and naught, the only two cusps. And we have the double number of side classes. I think we need to write it up, and then so I'll just find the side classes we had in gamma naught of 3, and then see how to double them up. So side classes, the identity S, and then I believe it was TS and T squared S, or the other way around. I'll make a break and find out about that. I have it here, gamma naught of level 3, generate the side class identity, S to minus first, T to minus first, S to minus first, and T S to minus first, which I have written here. So let's guess that the side classes of gamma 1 of 3 are plus minus all of those. I'll just put it into Mabel and check the 12 products and see that they don't lie in gamma naught of 3. That should be it. And then we can find the cusps afterwards. I have defined T and S, A2 and A3. And then plus minus the 3 guys. I even took identity in the group, that is basically not needed. But then we take the inverse of them times the others. And we can see that none of them lies in gamma 1. This is minus 1. And this is not naught. That's naught in the diagonal. So where do we have unity in the diagonal? Here we do, but then this isn't equivalent to naught. Neither is this. Here we see the duplicity. That means that my claim or my guess was correct. I didn't dare to make a claim. Finally, we shall check the inverses. How do they map infinity? That will give us the cusps. So it's st and st to minus first, but they already map infinity to naught. So plus minus do the same. So we still have the cusps, only the cusps naught and infinity. So that was the case n equals 3, cusps naught and infinity. N equals 4. Well, would that be the same? I'm inclined to thinking so. We have the isomorphism gamma naught of 4 being isomorphic to gamma of level 2. We did have this in some problem. I think I found it, by the way. Was it 18? No. Oh, it's in here. Here we have the isomorphism. And that, of course, leads to the same. It must be plus minus again. I won't do the details, so we should have the same cusps, like minus 1/2, naught, and infinity. And of course, t squared worked here, which should make t work in, yes, that lies in the group. Of course it does. So I'll just say it's infinity, naught, and 1/2. That was A. And this we really already noted in problem 3, or it's kind of necessary. Which of the cusps, if any, are irregular? naught is mapped to infinity by S. I will just go through the motions. Alpha equals S, then alpha minus first of naught is infinity. We have to look up, I didn't put up problem 3, it was the that's really a long section. Here we've got it. Alpha to minus first t to h alpha. We must find the smallest h for which plus minus this guy lies in the group, and that is here gamma 1 of 3 or gamma 1 of 4. Let's take 3 first. And then do the same with the cusp 1/2. Infinity mapping to 1/2. And then we must complete it could do like that. Minus 1 plus 2, meaning alpha is, guess it's minus 1, 1, minus 1, 2, is that right? That gives naught. It's surprising I can keep doing that. Minus 1, 1, and then it should be the same, just changing signs. Why isn't that true? Minus 1, 2, 2 minus 1, naught, and naught. All right. Oh, I did it the opposite way around, didn't I? Now, this maps infinity to 1/2. So this should map 1/2 times minus 2, that's minus 1 plus 1, the denominator vanishes. So this is a in the inverse, and then this is a itself. Then we have the inverse of alpha maps 1/2 to infinity. I'll make a break and do this in Mabel and then show you the result. Well, I've done what I said. I went with the same definitions and computed s to minus first ts and various powers of t. They all have diagonal unity, and then it's minus 1, minus 2, minus 3. So this guy lies in gamma 1 of level 3. So it has ramification index 3, but since it's a plus, it's regular. I will just write that. N equals 3. Ramification ramification index, that's impossible, 3, and it's regular. All right. Now let's look at n equals 4. There we have our alpha, which I called A, and then we do the same. Yeah, it's actually equivalent to unity, but we have -1 here. Oops. This is equivalent to unity as well, but we have 2, 3, and down here we actually get 1 lying in gamma 1 of level 4. So it has ramification index 4, and it's with a plus sign. So we have ramification index 4, and it's regular as well. I believe that finishes the problem, or solves the problem, and I'm ready for a cup of coffee.